all your app links belong to us. Understanding the threats of instant app-based attacks. I'm Yutian Tang from ShanghaiTech University. This is joint work with Yulei, Haoyu, Wang, Xiapu, Zhou, and Zhou. Mobile and mobile apps have become the main way that we communicate each and every day. As a study showed that the users spend more time on their mobile devices. Normally, the users spend around 3 hours on their mobile phone and only 2 hours on desktop. Mobile apps becomes the new interface for websites, as they have the shorter loading time, customer design, and there are millions of apps that are available on the smartphone market. But till now, apps cannot fully replace websites yet, as apps sitting in one garden and also difficult to navigate across apps. It can be hard to search and access in-app content globally. Thus, for a long time, we were living in an environment that we have both apps and mobile websites. They complement to each other and likely to coexist for a long time. The communication between the website and the app is performed by Android via deep links. So a deep link is kind of URL that points to the specific page inside an app. For example, if we search a place on Google, it returns a list of results. Let's see, we select this one, and we have several buttons: the call button, direction button. If we click the call button, it will redirect to the phone call app. If we click the direction button, it will use the default map to show the direction. Thus, it jumps starting from the web page and then move to a specific app. So this action is fully performed by the deep link. The first version of mobile deep link is called Scheme URL. It is fully designed for functionality without any security features. An app can design and define their own scheme to the OS. For example, a Facebook app defines FB as their scheme. They can use the scheme in the intent filter to say that they can process all the URLs that start with FB. So if we have a URL like this and we click this, and Android will find that the Facebook can process this URL. It will use a Facebook app to respond to this URL. But the problem is that not only Facebook can register this scheme, every app can register this scheme. Thus, a malicious app can register the FB scheme. If a device install a malicious app and then click this link, they may be lead to the malicious app. So Google noticed this. In the second version, they designed something called App Link. This time, they only support HTTP and HTTPS links. So no customer schemes, and it's also an additional verification scheme. So we want to start from the web page and then move to an app. The verification is conducted. If you want to open the Facebook app to respond to this Facebook link, the Facebook app has been verified that they really own this link. So is this secure? The answer is no. Actually, we found by leveraging a new type of app called instant app, we can launch attacks. Instant app is a new type of app that people can use an app without installing it first. For example, in this game, we just click the try now button. We can use the game without installing the game app. So the instant app is organized by modules. So an instant app can have only one base module, and it's optional to own some feature modules. So when all these modules are developed, they're published to the Google Play. To use instant app, user only need to click a specific URL, and the module is downloaded and launched. For example, if we want to use the Google Trip Instant app, we only need to click this URL, and the specific module is downloaded from the Google Play and launched. From user side, you see when we click a URL, a specific app is opened, but actually you do not go to the Google Play to download it. So our malicious app is uploaded to Google Play as already bypassed the Google Play security checking. So our malicious app contains two modules. One is the benign module, one is phishing module. So the benign module contains the basic function, all the things that we design for the user. It does not do anything harm. But for the phishing module, we try to simulate a login page. In the login page, we ask users to type in their password. So in this study, we define 3 attacks. We will introduce them separately. The first attack called link hijacking with STS. STS is short for Smart Text Selection. It's introduced in Android 8. So we will select a specific text, and Android will suggest what we should do next. For example, if we select series of numbers, Android will suggest, do you need to make a phone call, as they think a serious number, maybe a phone number. So in this study, we will select this URL with Smart Text Selection. The Android will suggest our malicious app. If the user uses our malicious app to respond to this URL, he or she can be hijacked. Here is the setting for the malicious app. We have two main intent factors. The first intent factor is from the benign module, so it's just tell the Android system that it's an instant app. We do not do anything harm. And we also have a deep link. The deep link is designed as follows. That in the deep link, we see that we can process all the YEP URLs. As Android do not verify any deep link, so the app can be installed correctly. So in Android, if a URL is selected, Android will look up for all the apps that can respond to the URL. So as we previously mentioned that we can process the YEP URL. So the Smart Text Selection will suggest our app as a candidate to respond to the YEP URL. Thus, when we select the YEP URL with Smart Text Selection, Android will suggest us. The second attack is called link hijacking without Smart Text Selection. In this attack, when a user click a URL in an app, for example, they click a URL in the Message app, and he or she will be redirected to our malicious app. So the setting for the manifest file is the same as previous. We do not make any explanation here. So in this case, we assume that this app is already installed from Google Play, and when the user click a URL, Android will check which activity can respond to this URL. So it relies on the method called the TrueSpec activity method. So next we will introduce how the TrueSpec activity method works. So the TrueSpec activity method contains 5 tasks. The first task is to rank all the candidate activity based on their app's package name. The second is check whether one app owns a higher priority. If no, it will check whether there is a saved preference app. If the answer is also no, it will use the first instant app to respond to the URL. Last, it will return a list of apps that can respond to the URL to let user to select them. So here is the problem. As we can see that step 4 is use an instant app. That means instant app has higher priority than a normal app, right? That is, if we have an instant app, we always have higher priority. recall this. Even if we have the YEP app, we also have the malicious instant app. As our malicious instant app have higher priority, it always responds to this URL. That's the reason this attack can be launched. The last attack is called instant app hijacking. So in this attack, we want to stop users from using any instant app. So the victim app is instant apps. For example, if a user wants to open the Google Trip instant app, he or she have to click this URL to open the Google Trip instant app. But in our attack, when he or she click this URL, he or she will lead to our malicious instant app rather than the victim instant app. So recall the TrueSpecs activity. Now we have two instant apps. From one, we can see that all these packages are ranked by the package name. That means if we have a smaller package name, we can rank higher. For two instant apps, their priority are the same, right? So we only need to design a malicious instant app with smaller package name. So we set our package name is a.b.xxx. So it's smaller than the com, the Google, the Android, or something, right? So for this part, our malicious instant app is ranked higher than the victim instant app. Thus, the system will use our malicious instant app to open this link. The attack is launched. In summary, in this study, we found two main vulnerabilities. The first is that they always said that instant app has higher priority than the normal app. And that's the second thing we found that if there are multiple instant apps, they are ranked by the package name, right? So the one with higher package name is responsible first. So to detect whether the existing apps are vulnerable to our attacks, we define a tool called the VDetector, which is built upon FlowJoy. We define a new type of program dependency graph called the UI-oriented program dependency graph. We embed a lot of UI information, including their labels, their types, their IDs, or their calling contacts, or even the activity context information. Due to time restriction, we do not have too much time to introduce how this tool is designed and how this tool works. We already open source it, and in the paper you can find how this tool is designed and how to use these tools to detect the attacks. So we skip this part and introduce the experiment. In experiment, we have 200,000 Google Play apps and 200,000 Tencent Map apps. So in the first research question, we see whether the existing apps are correctly configured their app links. We found around 80% Google Play apps correctly configure their app links. Around 3% Tencent apps correctly configure their app links. So here we list several common errors: incorrect JSON format, incorrect fields, incorrect namespace. We have to highlight that no matter the app correctly or not correctly or incorrectly configure their app links, they are all vulnerable to our attacks. In this research question, we just want to see the status and how the developers works at this stage. And if an app is not correctly configured their app links, they are more vulnerable. A lot of attacks can be launched, right? The second research question we discussed are the existing apps robust to the link hijacking attacks with STS? So still this data set, we found around 26% of Google Play apps are vulnerable to link hijacking attacks with STS. Around 27 Tencent apps are vulnerable to link hijacking with STS. For research question 3, we see whether the existing apps are robust to link hijacking attacks without STS. Based on the same data set, we found around 28% of Google Play apps are vulnerable to link hijacking attacks without STS. Around 31% of Tencent apps are vulnerable to link hijacking attacks without STS. So in the fourth research question, we see whether the existing instant apps are robust to instant app hijacking attacks. We found that all instant apps are vulnerable to instant hijacking attacks. In the fifth research question, we see the accuracy of our tool. We found that we select 800 apps from Google Play and then manually check whether they can be attacked. Our tool reports 276 vulnerable apps, and all these apps reported by our tool can be exploited. Thus, the precision is 100%. Also, we found that we're missing some apps. Thus, the recall is around 87%. The missing app come from two categories. The first category is they use native code. So they use, for some apps, they are game apps. They use C or C++ code to organize their UI elements. And also some apps, they use third-party UI framework rather than the default one. So for this kind of app, we cannot detect it. Countermeasure. Actually, we provide 4 solutions to allow users to prevent developers from all these type of attacks. All this based on that as we have to select a specific attacks or click attacks to launch attacks, specific URL to launch attacks, right? So we do this to stop users from selecting any tags or to not make any suggestions for STS or stop them from clicking and all these sorts of things. But actually, these solutions do not solve the problem from the root. Thus, we define a new type of URL called verified domain package. So it starts from the start activity for results, which is a basic API in Android. We get the package name, get the signature, and download the DLL file and do the verification and try to see if they claim any URL they do not own. If we found this, we report the case. Okay, thank you. That's all.